Not gonna lie, this is like try 4 of this recording. So let's do it. We are on 4.4. Oh, 4.4, try 4. Maybe that is fitting. And we are talking about Riemann sums. And I don't know if it's Riemann or Riemann or how to exactly say that, but maybe in my next class I will take some time on the internet to figure that out and get it right. But you know, we have some learning objectives and some homeworks. And without further ado, we're going to get into it. So big picture here is that we are on a journey of math understanding, and we want to understand what an integral means. So we know what derivatives mean, right? We know that derivative is the slope of a tangent line at a point. We don't have that same kind of background idea for integration. So big picture, that is where we're getting, okay? But we need to start that journey with this idea of sigma notation, which is used when we want to find the sum of terms that are related in some way. For instance, say we wanted to find the sum of the first 10 numbers. We could simply write out all of our terms and add them up. 1 plus 2 plus 3 plus 4 all the way up to 10. I was going to say more, but it was a mouthful. What if we wanted to, okay, so sums of the first 10 numbers, not too bad, doable. But what about if it was the first 100 numbers? That one I'm definitely not going to say. Suddenly, it is much more cumbersome to write out and add up all of our terms. This is where the idea of sigma notation comes in. And we use a capital sigma, which is a Greek letter denoted as this E thing, to represent sum. I'm not very good at drawing them, but that's kind of how I do it. So here's our formal definition of sigma notation. The sum of n terms, a1, a2, a3, all the way up to an, is written as the sum of I equals 1 to n of a sub I, which is equal to a1 plus a2 plus all the way up to an. I is the index of summation, a sub I is the ith term of the sum, and the upper and lower bounds of summation are n and 1. So we can see 1 to n, upper and lower bounds, just like when we were doing integration, just like when we learned definite integrals. Note, the upper and lower bounds of summation must be constant with respect to the index of summation. However, the lower bound does not have to be 1. Any integer less than or equal to the upper bound is legit. So what would sigma notation for the sum of the first 100 numbers look like? Well, it would be the sum from I is equal to 1, where we're starting, to 100 of I, which indicates that we just kind of plug in whatever is in I until we get all the way up to our top term. So this would indicate, okay, I is equal to 1, and then, you know, sigma indicates plus, and then we rotate to our next term, which is 2, and then we know that it's plus. We know this is all going to be sums, plus 3, plus all the way up to plus 100. So it doesn't actually make the math easier. Like, it's not a shortcut to adding 1 through 100, but it's a shorthand way of writing it. Summation is shorthand for writing large sums. Oh, look, I got ahead of myself. The sigma notation is a more concise way for us to represent large sums. That said, there's a little bit of variation in the way that sigmas are written. We see some other letters kind of floating around and invited to the party. So for instance, we might see something like the sum. Oh, that was a really bad one. I'm just going to retry there. The sum of n equals 1 to 3 of 2n minus 1. In this case, we're not starting our index at I equals 1, but rather at n equals 1. And what it's getting at is that this and this, they got to match, okay? And so that's kind of what it was saying up here when we talked about the upper and lower bounds must be consistent with respect to the index of summation. But anyway, so we evaluate this in the same way, even though it looks different, okay? So when n equals 1, we just plug it in. 2 times 1 plus, or not plus, minus 1 is going to equal 2 times 1 minus 1 is equal to 1. 2 times 2 minus 1 is equal to 3. 3 times 2 times 1. Apple Pencil, why are you not working? Sorry. I hate wasting lecture time when my technology fails. Okay, 2 times 1 minus 1 is equal to 1. 2 times 2 minus 1 is equal to 3. And 2 times 3 minus 1 is equal to 5. And then we know summation means sum, adding. So 1 plus 3 plus 5 is equal to 9. What about the sum from n equals 1 to 4 of n squared? We're going to write that as the sum from n equals 1 to 4 of n squared, which is equal to 1 squared plus 2 squared plus 3 squared plus 4 squared, which happens to be equal to 30. And I'm not actually doing that mental math that fast, although I should have told you that I was. But anyway, we can use any letter we want for our index. So the sum of r minus 1, the sum of r minus 1 from r equals 4 to r equals 6. That would be 4 minus 1 plus 5 minus 1 plus 6 minus 1. And then that is, in fact, equal to 3 plus 4 plus 5, which is equals 12. Or the sum from k equals 3 to 5 of k times k plus 1. I'm going to let you guys try this one. But the answer that you should get, and pause this and try to get this answer, is equal to 62. Okay. Scrolling down. Sometimes there's more than one variable in a summation expression. For instance, the sum of n equals 1 minus 4 of, I think I should say the sum from n equals 1 to 4, and I'm actually going to change that. So the sum from n equals 1 to 4 of k over n plus 1. So our index in this case is n and not k, but we need to plug our variables into n. K remains unknown, so there will be k's in our final summation answer, right? So we know the sum from n equals 1 to 4 of k over n plus 1. We're starting at n equals 1 and going to n equals 4. So is equal to n equals 1 plus 1, k over 1 plus 1, plus 2 plus 1 over k, and k's on top, plus 3 plus 1, k plus 4 plus 1. So we went from n equals 1 to 4, and we ended up with k over 2 plus k over 3 plus k over 4 plus k over 5. And that would be your final answer because you don't really know anything about k in this specific instance. So really just keep in the back of your head that this guy right here means sum. Keep that in the back of your mind, and now we're going to move forward to part 2, Riemann sum approximations. So imagine that you were given some general curve y equals f of x. I'm just going to draw it as this, y equals f of x. And for reasons that will be made clear in your future, you're asked about finding the area under said curve from like, here to here maybe, arbitrary points. But you want to find the area from under your curve to above your x-axis. And right away, it might seem obvious to you that you would maybe want to use certain shapes, like maybe rectangles that have a very easy area to find, to kind of break this into pieces. And then if we could find the area of those rectangles, maybe we could get an approximate area under the curve. And that is actually exactly what we are going to do with this idea of something called a Riemann sum. So we're going to jump right into an example, actually. So I'm going to scroll down and see if I can get this on one page. Let me make my window bigger, and I can. All right. Approximate the area under the curve f of x equals x squared plus 1 between 1 and 3. What does this look like? So like every good mathematician, we are going to start with nothing more than a picture. So here is our axes, and I know that we are going from 1 to 3, so I need more room over here. And I know that x squared plus 1 is a parabola at 1, so I'm going to sketch that out like this, from 1 to 3. And that is what it looks like. And I'll draw even lines here so that I can really see what area I'm trying to approximate. We are going to approximate the area under this curve using 4 rectangles of equal width under the curve. So we know that we have this 1, 2, 3, 4. And there will always be some sort of tell in the problem about how many rectangles you're going to use to approximate area. In this case, we're using 4 rectangles of equal width. So I see that I'm going from 1 to 3. And so I know that 3 minus 1 over the number of rectangles that you have will get that you're asked to will give you your increments, which we will actually call delta x, okay? So 3 minus 1 will give me 2 over 4, which is equal to. So I'm going to try to mesh this with iMovie, but I did actually add a hat, so I kind of ruined my consistency here, but bear with me. So we know that the width, which we are going to call delta x, is going to be 1/2 or 0.5. And as we can see, if we use that increment right here and right here, we do in fact get 4 rectangles of equal width, which is what we wanted. So in order to calculate the area of a rectangle, we need 2 things, right? We need the width, which we have, and we also need a height. And if we look at this function and we carefully construct some rectangles, we could have convenient heights that we could find easily using perhaps the function. So for in this example, we're going to use what we call a left Riemann sum, because we're going to use the left endpoint of each of our increments. So I'm going to draw the left endpoint and make it into a rectangle, and hopefully you can see we have 1 rectangle here, 2, 3, and 4. Okay, we know that the width of each of these rectangles is going to be 0.5. And the height of these rectangles, maybe you can see, conveniently falls right on our function x squared plus 1. So the height of rectangle 1 is going to be f of 1. The height of rectangle 2 is going to be f of 1.5. The height of rectangle 3 is going to be f of 2. And the height of rectangle 4 is going to be f of 2.5. And now to evaluate f of 1, 1.5, 2, 2.5, we just plug in 1, 1.5, 2, 2.5 into f of x, right? So f of 1 equals 1 squared plus 1, which is equal to 2. F of 1.5 equals 1.5 squared plus 1, which is equal to something that I'm going to calculate right now, which is going to be 1.5 times 1.5, 2.25 plus 1 equals 3.25. And I actually made convenient spaces for this. So f of 1 was 2, f of 1.5 was 3.25, f of 2 is going to be 4 plus 1, which is 5, and f of 2.5 is going to be 2.5 squared plus 1, which is going to be 2.5 times 2.5 plus 1, 7.25. And then if we multiply the width times the height, we can get area. So we're going to get 1.625, 2.5, and 3.625. And if we add those all together, our total approximate area under the curve is going to be 8.75. Okay, so the approximation of the area under the curve using the area of rectangles is called a Riemann sum. So you just did a problem involving a Riemann sum. Congrats. Since Riemann sums approximate area, they aren't equal to the exact area. Sometimes they're larger, called an overestimate, and sometimes they're smaller, called an underestimate. Hopefully you can see that using the left endpoint gave us an underestimate, because look at this, these red triangles that I'm filling in are area under the curve that was not accounted for. If we had chosen to use the right endpoint, we would get an overestimate, because now those triangles in yellow would be our right endpoint, and that would be extra area that we accounted for. So we're gonna talk in the future about like ways we can meet in the middle, but for now you're kind of stuck with overestimates or underestimates, okay? So we're going to actually generalize this process with an arbitrary function with arbitrary boundaries using an arbitrary amount of rectangles. So we are going to draw a nice big picture here where we have, oh my God, that was terrible. I'm gonna try again. Where we have a function y equals f of x, and we are going to start at a, and we're going to go to b, so we're taking a Riemann sum from a to b, and we are going to break it into some increments. I'm going to start with x of 1, x of 2, dot, 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 all the way to x, and then b. So now we have triangles, or not triangles, rectangles from having created that. And those are going to be, we're going to call a x sub 0. And so therefore f of a is equal to f of x sub 0. And then over here we'll have f of x sub 1, f of x sub 2, right? The value at the function at our x values of x sub 1, x sub 2, a. Then we know that our width is going to be called delta x. These are the widths of our rectangles. And so approximate area is equal to the area of rectangle 1, which we're going to call this guy, 2 plus 2 plus dot, 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 all the way to area of rectangle n. And so the height will be the value of function at left or right endpoint, and the width is delta x. Okay, so this is kind of just a general picture of what we already did in case you wanted to see it in terms of like just x sub 1, x sub 2, with delta x again being our width. And then we have down here kind of a conclusion that we could draw. Given a strictly decreasing function, so only going down, a left Riemann sum, so using the left endpoints on a decreasing function, will give you an overestimate because you see you have extra area, and a right Riemann sum will give you an underestimate because you wouldn't have enough. And then an increasing function, so if our function is going the other way, a left sum will actually give you an underestimate, and a right sum would give you an overestimate. Given strictly decreasing and strictly increasing. Obviously, if they're wiggling around like that, then you can't make any generalizations. And now we're going to do two practice problems. So approximate the area between the x-axis and the graph of f of x equals 2 to the x. Desmos, let's check this out. Free beautiful math, love that. Graphing calculator. We are going to have y equals 2 to the x. Okay. And we know our function looks like this, generally from -3 to 3, using a right Riemann sum with 3 equal subdivisions. So -3 minus 3 over 3 equal subdivisions, -6 over 3 is equal to 2. So, well, -2, but it doesn't make sense to have negative increments. So just doing that math, let's sketch out our function. We're going from -3 to 3. Our graph looks more or less like that. -3, -2, -1, 1, 1, 2, 3. We're going from here to here, and we know that our increments will be 2. So here's one rectangle, 1, 2. Here's another rectangle, and we have 3 equal subdivisions, and we are using a right Riemann sum. So here's the right endpoint. Draw a rectangle, right endpoint, draw a rectangle, right endpoint, draw a rectangle. Okay, so now we know delta x is equal to the width, which is 2. And then the heights are going to be the right endpoint. So the right endpoint 1 is going to be f of -1. So rectangle 1 area is going to be 2 times f of -1. F of -1 equals 2 to the -1 equals 1/2. So this is going to be 2 times 1/2, which is equal to 1. Rectangle 2, I'll label these here, is going to be 2 times f of 1 equals 2 times f of 2 is going to be 2 to the 2, which is equal to 4. So 2 times 4 is equal to 8 is going to be the area of rectangle 2. And then rectangle 3, we are going to have 2 times 2. This was 1. Excuse me. Sometimes those basic calculations really get you. And then number 3, you're going to have 2 times f of, your right endpoint is 3. Let's check f of 3 is going to be equal to 2 to the 3rd, which is equal to 8. So this is going to be equal to 2 times 8, which is equal to 16. And then our total area is going to be 16 plus 4 plus 1, which is equal to 21. And so Our approximated area under the curve is 21. And as you can see, this is a pretty bad estimate because we have all this extra space right here, and right here. But, you know, take it with a grain of salt. And now I want you guys to go ahead and try this last one, and we will start class with approximating this area. So thank you for watching. Have a lovely weekend, and that's all I got for you guys.